Hello everyone, it's already 6 pm, so I'll start the session. Let me introduce myself first. I am Ananya. I am a PhD student in the Department of Electrical Engineering, IIT Kanpur. Welcome to the live session for the course Introduction to Semiconductor Devices. This is week 10 and I will be the TA for this session. So I always conduct the session on every Tuesday from 6 to 8. And in this session what we do, we'll discuss about the topics those were discussed in the week. Today we'll discuss about the content of week 10 and we will discuss few questions and solutions, and the questions are supposed to help you in solving your assignments. So the questions are similar, the assignments you got in your the questions you get in your assignments. Okay, so let's start the session. People can join in the middle also. So this is week 10. We have already done 9 live sessions. I hope that some of you have attended my live sessions and hopefully you are getting some benefits from these live sessions. So today we will discuss about MOSFET, and we are discussing about MOS capacitors and MOSFETs in last couple of weeks. So today we will discuss some theoretical concepts, mainly like related to MOSFET scaling and what are the problems that come into the picture when we talk about MOSFET scaling. We will discuss about those, short channel effect, narrow channel effect, all those concepts, and this will be mostly like we'll discuss the theory part of it, will not go into the details of the mathematics, like how to do the derivations of the equations, like in certain cases the threshold voltage expression, the current expression, all these things changes little bit compared to traditional long channel MOSFETs, but we will not go into the details of it because the course content has been designed in such a way that the idea is to give you like overall picture, a broad picture, rather than like going into too much mathematics. Okay, so in this week first professor has discussed about MOSFET scaling. Okay, what is MOSFET scaling? Basically like earlier when say for earlier technology nodes, MOSFET scaling means multiplying the different lateral and vertical dimensions of MOSFET with a particular factor. Not only that, also all other parameters like supply voltage and doping concentration, all these things are also changed with that factor. It may be either increase or decrease by that factor. Okay, so that factor we consider as alpha, so that is known as the scaling factor. alpha. So alpha is typically zero point 0.7. If you remember, you can go through the lecture videos and lecture notes. You can see that from one technology node to another technology node, when we go, typically the scaling factor alpha is zero point 0.7. There is a reason for it. I mean, ultimately we want to reduce the MOSFET area by 2, right? Okay, what is area? Area is like W into L. This is a general definition of area. I'm not considering the channel length, or this W may not be channel length. This this W is not channel width, or L is not channel length. This is like normally area, how we do W into L, like width into length. So if we reduce W by 1 by square root, and if we reduce if we multiply L with 1 by root 2, then our final area will be A by 2, right? A dash by 2. Okay, so 1 by root 2 is roughly equal to 0.707. So that is why the scaling factor is 0.7. Okay, ultimately we reduce the overall area of the MOSFET by 2. Okay, so what we do, we scale lateral and vertical dimensions. This can be, suppose initially we have L, and then we will multiply 0.7 to that, so that will be alpha L, alpha W, and so on, alpha TOX, all this. Okay, we also scale the voltages, so we reduce the voltage. We are scaling means alpha is less than 1, so we are scaling means we are reducing the lateral and vertical dimensions. We also reduce the voltages. So from VDD, what we do, alpha VDD, okay, we reduce the voltages. Threshold voltage is also changed because of this. But what we increase, actually one factor we increase, that is the doping concentration. So if it was earlier, say N, if I am considering a N MOSFET, say it has a p-type silicon substrate that has Na doping concentration, that will increase to Na by alpha. That will be multiplied by 2, square root 2. Okay, so why it is increased, basically we will discuss about different short channel effect today. And in short channel effect, if you remember from the class, normally what happens, threshold voltage decreases. Okay, we don't want a very low threshold voltage also. If you remember why we don't want a very low threshold voltage, because ideally if we want to operate our MOSFET as an on and off switch, then we want the on current and off current, that the ratio to be very high. If we decrease the threshold voltage to a very low value, then that we may not achieve. Okay, we will not achieve. So that is why we want to keep our threshold voltage a certain value, not too less. So because of that, that is also one reason, that is why we increase the doping concentration, because threshold voltage is related to doping concentration. And one more reason is that, if you remember, if our this is my source side N plus, and this is my drain side, I have my oxide and gate. This is my, say, p-type silicon substrate. If it is a NMOS, then there is a depletion layer here, right? This width of the depletion layer, that depends also on the doping concentration. And what happens in short channel MOSFETs, this depletion region that actually contributes to the overall depletion region of the channel, right? So we don't want a very high depletion region in this N plus P junction, between the source and substrate, and drain and substrate. Okay, if we increase the doping concentration, then this depletion width also will decrease, because higher the doping concentration, depletion less will be the depletion width. This we know from our knowledge of PN junction that we have studied. Okay, there are other reasons also. For example, there is one term called punch through that may also happen if the doping concentration is very low, because it was not discussed in the class, so I will also skip it. But there are certain reasons. Mainly for short channel MOSFETs, we want our doping concentration to be higher. Okay, that is why we increase the doping concentration, whereas other lateral and vertical dimensions as well as voltages are reduced by a factor. Now, what is the effect of MOSFET scaling? First we will see in MOSFET area. This we already know. We want to reduce the overall MOSFET area by 2. Okay, we want to make it half. That is why typically the scaling factor is 0.7, so that overall we get an area reduction by 2. Okay, so initially say if it was W into L, that will become alpha square WL. Okay, so 0.7 square is approximately, this is, I'll just write 0.5 because, okay, which is the area is reduced by 50%, right? Area become half. This is very important because now in the same area we can pack double the number of transistors. So overall our efficiency of our circuit, efficiency of our whatever, say if it is a motherboard or something, that will increase because number of transistors are double now. Okay. Next is gate capacitance. So this is CG I'm denoting. So this is COX. This is the overall gate capacitance. We multiply with the area because COX is gate capacitance per unit area, right? So this is again epsilon OX by TOX into W into L, right? So what will become? So TOX we reduce, again we multiply with alpha, so that is alpha, and this is alpha square. So overall we have alpha into, if my initial gate capacitance is CG, so you will get alpha into CG, so that means 0.7 into CG. So that means our gate capacitance reduced by 30%. Similarly, what will happen to COX dash? Say initially it was COX, it will become reduced. So that is epsilon OX by TOX. TOX is multiplied by alpha, so that is 1 by 0.7, right? 1 by 0.7, whatever the initial oxide capacitance per unit area. So this is also get reduced. Oh, this is not reduced, this is increased. By roughly say 40%. Okay. Next, what will happen to current? So we are mostly considering our devices as on-off switch. So I will use the expression for saturation current, which is mu cox W by L, twice L actually, VGS minus VT square. Okay, so mu is a material parameter that is constant. COX, this is we will get this 0.7. W is also scaled by alpha, L is also scaled by alpha, that will go away, and these are also scaled by alpha, so total there will be 0.7 square. So that means our ID dash will be 0.7 into ID, right, original ID. So this is also reduced by 30%. Next, the important term for us is the delay in the circuit. Okay, delay in the circuit, that is basically how we our MOSFET is like a RC circuit. Okay, it has some resistance and it has some capacitance. Okay, and you know that the delay in the circuit, if you have studied about like RLC circuit, the delay comes from tau is equal to R into C, right? So T is equal to, that delay is equal to capacitance into resistance, that we will write it as V by I. Okay, so capacitance, overall capacitance is decreased by 0.7 factor, so that will give us this 0.7. Voltage is decreased by 0.7, and then current I is also decreased by 0.7. So overall our delay reduced by 30%, right? Delay, there will be a multiplication factor of 0.7, that means it is getting reduced to compared to the original delay. Okay, so this is again important for us. As our delay is getting reduced, we can switch our device, switch our MOSFET faster. Okay, so overall the performance of our circuit is getting improved, the frequency of our circuit getting improved. Okay, if you try to connect like a very old circuit, like if if you are from ECE background and if you have done some Verilog VHDL coding, if you try to connect a very old circuit, old board to your computer or to some other device which has a circuit that is like latest, the connection will not be proper, because the frequency of one circuit is much higher compared to the other one. Okay, so all the newer devices have much higher frequency, and because of that the computation power, the computation speed has improved, and that is why MOSFET scaling is so important, and that is why because of the scaling you can see so much of improvement in efficiency of electronic devices, electronic circuits. Okay, so this is important for us. Next term is the power consumption. I will write somewhere here. Okay, let's see. Power dissipation. So this is the dynamic power dissipation. So the formula is CV square into frequency. Okay. This is 0.7. V is 0.7 square. The factor is 0.7 square. And frequency is like this inverse of tau, right? So that is again 0.7. So this factor is 0.7 square, so this is roughly 50%. Okay, so power dissipation is also reduced by 50%. Okay, so that I mean, because of that, because of scaling, we are getting disadvantages, right? Our area is getting reduced, so we can add more and more transistor in same area if we keep the area constant. Delay of the circuit is getting reduced, so our operating frequency is being improved. Okay, and then power dissipation is also getting reduced, so overall there will be less power consumption by our circuit. Okay, there will be less heat generated by our circuit. If our power dissipation is more, then our circuit will heat up more easily, and we don't want that. Okay, so these are the advantages of MOSFET scaling, and based on that scaling, different technology nodes are defined. So what is technology node? Technology node, you must have heard about this different technologies, 180 nanometer, now we have 5 nanometer, even 2 nanometer technology also. What is technology node? This is the smallest, I mean, it is defined as the smallest dimension a technology can make. Okay? Technology can fabricate. Earlier it was defined as the gate length. It may not be exactly the gate length as we are going towards more and more scaling. Okay. Now, this is one type of scaling that we have discussed, where we scale the device dimensions as well as the voltages. There is another type of scaling that is known as constant voltage scaling. Okay. Why we are discussing this constant voltage scaling, and why people have moved to this constant voltage scaling? Because voltage scaling is not easy, right? If we want to scale the voltage, say we are decreasing the supply voltage, we are supplying the voltage with some external circuit. Okay, we are driving our transistor with some external circuit. Overall, our circuit, transistor circuit, is connected to external world with some other circuitry, right? If we want to change the voltage of everything, we have to change all the external circuits also, which is not economically feasible, and it's not a very smart decision to do. That is why people moved into this constant voltage scaling. Okay, so voltage is not easy to scale always. We need to change all other peripheral circuits. Another reason, as I mentioned, why voltages, we don't want to scale our voltages, because we don't want to reduce our VTH. Okay, we cannot reduce VTH to a very low value. Please go through the lecture notes where the graph is given. I mean, when the current is plotted in log scale. Okay, with the sub threshold slope, where you can see that 60 millivolt per decade, there you will see that we actually have sometimes significant amount of current below threshold voltage, even if we ideally want it to be zero. Okay, but nothing is ideal. There will be some leakage current, and we will get some I off. Okay, so if our threshold voltage is very low, then our I off to ion ratio will be also less. We don't want that for switching application if we are using our transistor for digital applications, right, as a switch. Okay, that is why nowadays constant voltage scaling is uh, used. Actually, the way the scaling was done earlier, that is not uh, that's not how it is done nowadays. This was discussed in the class, if you remember, because there are many problems when you want to. It is not as simple as that we want to reduce the dimensions by a factor. Okay, there are most of the concepts that we have studied in long channel devices, they may not be valid if we decrease the dimensions the way it was scaled earlier. Okay, there are many non-idealities come, and because of that this concept of scaling is different now. But we are not discussing those things. I mean, I also don't know much about it because this happens in industry levels. I don't know, like, we know this is how the traditional scaling is done in MOSFETs, okay, at least in earlier technology nodes. Next we will discuss about short channel MOSFET. We are scaling our devices significantly as I mean, when our channel length become less than a micron or so, many things that we have already discussed for long channel devices are not valid. Okay, so that is why discussing the short channel effects is very important, so that you get an idea that even though we have studied long channel MOSFETs, although the concepts are still valid, there are some non-idealities when we talk about the MOSFETs of today's generation. Okay. There is no exact definition of this short channel MOSFET, but typically L is less than 1 micrometer, that we can consider. Okay, when the channel length is in nanometer dimension, many non-ideal things happen. Okay, we will discuss. And another definition of short channel MOSFET is when channel length L is comparable to depletion region. What depletion region? Say this is our MOSFET. We have N plus source, N plus drain, P silicon substrate if it is a NMOS. We have this oxide layer, we have this gate terminal. There is certain depletion width here, because ultimately this is a P plus N plus P junction. This is a N plus P junction, and we always try to what we do, we keep this junction as reverse bias. Okay, we don't want a current conduction in this junction. Okay, we want current conduction in our channel, so this is always reverse bias, so there will be a significant depletion region, and that depletion region will be mostly in the p-type silicon substrate, because the doping concentration is less. We know that wherever the doping concentration is less, depletion width will be more. Okay, so let's say this depletion width is xd. I'm neglecting the depletion width in the n plus side, so L is comparable to depletion region, means this xd is comparable to M. Okay, so in this case we can say that this is our short channel MOSFET. Now in the class it was discussed how the IV characteristics of short channel MOSFET looks like even when our W by L is constant. So W by L is constant for the short channel MOSFET, and the comparison was given with respect to a long channel MOSFET with the same W by L ratio. What were the observations? Observations were that in short channel MOSFET, what happens, the saturation current ID set increases linearly with VGS. For long channel MOSFET, you remember the ID set current expression, right? We have this square dependency of the drain current if we look like if we compare this VGS, but in short channel MOSFET the ID set actually increases linearly with VGS, not by square. Okay. Another observation was that VD set looks constant. Okay. For long channel MOSFET, what is VD set? VD set is equal to VGS minus VT, right? So as VGS increases, VD set also increases in case of long channel MOSFET, but in case of short channel MOSFET, VD set looks constant even if our VGS is varied. Okay. Why? We will discuss about this one by one. Then next is ID is much lower compared to long channel MOSFET. ID set, overall the drain current is much lower. Even though, so ID is much lower compared to long channel. Compared to long channel MOSFET. Long channel MOSFET, even though W by L ratio is same. Okay, so mu is same, but it's a material parameter. COX, say this is also in the same range, W by L is same. VGS, for similar VGS and VTH value, current is still low for short channel MOSFET compared to long channel MOSFET. Now why these things happen? What are the reasons behind this? So what are the non-idealities happen we observe in short channel MOSFET? So first is velocity saturation effect. In last week we discussed one problem where I discussed about velocity saturation effect. Okay, what is velocity saturation? We know this formula, right? Drift velocity for electrons or holes is equal to mu into electric field, right? But this formula actually is true under certain condition. Okay, so if we plot electric field, which is in say volt per centimeter, and drift velocity Vt for electrons or hole, let's consider for electrons, say this is centimeter per second, then drift velocity, this graph will look like something like this. Okay, initially the drift velocity increases linearly with electric field. Okay, and the slope of this is this mu. This is like a y equal to mx kind of a equation, right? The slope is mu. The slope is mu in this linear regime. So mobility mu we define only in the linear regime of this Vd versus electric field graph. Beyond that point, beyond a certain electric field, so this is known as the critical electric field, the drift velocity actually constant. Okay, why it is constant? Because when the electric field is very high, then the electrons will collide with each other. It will try to move in a faster speed, right? It will try to move in a higher drift velocity, but then it will collide with another electron, it will collide with other atoms. Not directly collide, its parts will be deflected. So these phenomena is known as scattering. So this velocity saturation, this constant velocity, drift velocity, which is known as Vd said, this happens due to scattering. Okay, even though we are applying a lot of electric field, the electrons will not be able to move as fast as we want. Okay, this is because of scattering, and this is known as velocity saturation. Now this Vd set value is typically around 10 to the power 5 meter per second. Okay, Vd set value, and electrons actually cannot move faster than this value. Okay, approximately. This is for semiconductors. In case of metal it is a bit different, but we are considering only semiconductor. So for semiconductor, the value is in the range of 10 to the power 5 meter per second. Okay, this point is known as critical electric field. Now what is so we have our channel, this is n plus, this is n plus. Our electron is moving from source to drain, because in the drain side we are applying a positive bias, right? So what is the electric field this electron is experiencing? We have already considered that our vertical electric field is negligible. That is one consideration that we keep in our mind while doing the derivation of the current expression. You can go back to the last week content, you will see that this is one assumption. Our like this lateral electric field value is much higher compared to this electric field in the x direction. Okay, so this electric field is basically Vds by whatever the channel length. Okay, now if our channel length is less, our electric field will be much higher, that value will be much higher. Okay, if we have a long channel, we will get some electric field value for a range of Vds, say from E1 to E2. Okay, if it is a long channel, this electric field value will be less, because more L is higher, because so our electric field value will be less. So for long channel, most of the time we will not reach this critical electric field. We will mostly operate our device in this linear regime, where we can expect that our drift velocity increases linearly with the electric field. But what will happen if we are using a short channel? So L value is very small, our electric field value will be very high. For say certain Vds, our electric field is so high that it is higher than the critical electric field. Now we are expecting that whatever the electric field we are getting, we will try to multiply it with mu, and we think that that is our drift velocity. But drift velocity will not be that value. Drift velocity will saturate to this Vd sat value. So even though we are expecting a higher drift velocity, overall our drift velocity of the electrons will be less in short channel MOSFET. Now what will be the effect of it? So if you remember, how we calculate current? Current is equal to whatever the charge we have and tau, right? So our inversion charge was COX VGS minus VT. Basically our tau will be what is the time required for electrons to move from this side to this side. That will be earlier our tau expression was different. You can go back to the expression for tau when we are discussing long channel MOSFET. Now in this case, what will be our tau? Tau will be so drift velocity L by drift velocity, right? Okay. So our overall current will be, if we use that tau expression, so this will be VD set. Now what it means? It means that our I is directly proportional to VGS, not squared. There is no square term for it. Okay, so our current increases linearly with VGS. Okay, that is why in case of short channel MOSFET, there is a linear increase of current. Okay, even though if a long channel, it has a square dependence. Okay, now this part, why we already got the answer. Now why VD set looks constant? What is the VD set value for long channel? This is VGS minus VTH. But what is the VD set value for short channel MOSFET? Whatever the VDS we apply for which this critical electric field is reached. After that, VD set is constant, right? So drift velocity is constant, so our current is also constant. I mean, it will vary with VGS, but I mean, for a particular VDS value, it will not change. Okay, even if we change VDS. So what is VD set for VDS set for short channel MOSFET? This is the voltage where VDS is such that critical electric field is reached. So even if you change VGS, our VDS set will not change. Okay, it is some constant value. Okay, we know the L, whatever the channel length. We know the critical electric field. Okay, for say electrons, this is typically in the range 10 to the power 4 volt per centimeter. Okay, whatever the VDS value, that is the VD set for short channel devices. Okay, so this we already know, right? Next, before going into why ID is much lower, let's discuss another non-ideality in short channel MOSFET, that is the channel length modulation. Channel length modulation is present in long channel MOSFETs also, but this is more prominent in short channel MOSFET. Okay, this also I have briefly discussed in last class. Okay, so consider a scenario which is V set constant again. Okay, so what say we have some critical electric field. This is in the range say 10 to the power 4 volt per centimeter, typically in the range. Okay, this is for a particular material, inside a particular material. For electrons, this will be some value. Okay, now this electric field is reached because of the applied VDS, whatever the electric field along this channel, right? So electric field, what is electric field is V by L, right? So V by L, electric field is V by L. So in our case this voltage is VDS by L. So we know the channel length. It is a short channel, it will have some value, right? Less than 1 micrometer, some value it will have. Some critical electric field that is already known. I mean, people have done experiments based on that. Electric field is known. So if we multiply this electric field and this L, you will get some VDS. Whatever the VDS you get, that is the VDS, that is the VD set. This is a constant value. This electric field, the critical electric field, is a constant value for a particular material for electrons. Okay. So this VDS will be also constant, right? That is why it does not depend on VGS, unlike long channel. In case of long channel MOSFET, it depends on VGS. But in case of short channel MOSFET, it is a constant value and it does not depend on VGS. Okay, I hope it is clear. It is the voltage for which critical electric field is reached. Now channel length modulation is what? Let's consider a point after pinch off. Okay. Now say our channel is like this. I have very briefly discussed earlier. And this is my channel. There will be my depletion width like this. Okay. This depletion width will be more near in this side near VDS because we are applying a positive bias, and remember this is in reversed bias, this P silicon and this drain and source junctions. So the depletion width will be more this side, it will be less this side. Okay. Now our channel is like this. Originally our length of the channel was L. Now our length of the channel is L minus delta L, whatever this delta L is. Okay. So our channel after pinch off is L minus delta. So what happens? Our effective channel length decreases. How our current will change? Our ID dash will actually increase. This was our original ID. New ID is actually slightly more than that. So there is this, we can use Taylor series expansion for this L by L minus delta N. L that will give us 1 plus delta L by N. Okay. So this is ID 1 plus lambda. This is the channel length modulation parameter. Lambda is channel length modulation parameter multiplied by VDS. Okay, because it depends on VDS, right? How much this pinch off will happen, that depends on VDS. So that is why there is this VDS term, and this is the channel length modulation parameter. Now why there is an increase in current? If you remember, in the current expression we have this L which is like inversely proportional to current. Okay, so since our L is actually decreasing, overall our current is bit increasing. Okay, and remember this is after pinch off. That is why even though we are saying that after pinch off we have a constant current, but this is not actually constant. Like this, this slightly increases. Okay. So these are some non-idealities. increase. And this channel linked modulation, this is again prominent in case of short channel MOSFET, because in case of long channel, this L minus delta L, that value L is already very large, right? So this delta L is negligible. The channel length will not shrink like this, as I have shown in the figure. L is a large number for long channel MOSFET. This delta L is some small value after pinch off. So overall, this value delta L by L is a very small value for long channel. But in case of short channel MOSFET, again, this L is already a small value, right? So L minus delta L value, and because of that, the change in the drain current, that is significant. Okay, so that is why this is again more prominent in short channel MOSFET, especially when we do scaling of this, right? This is one effect. And next we will discuss why our current is actually ID is bit lower. That is due to mobility degradation. What is our ID expression? Mu COX W by L VGS minus VTH into VDS. This has a linear dependency. Now when we have large VGS, the vertical electric field, earlier what we have neglected, that is actually much higher. What we said earlier, that the electric field between the source and drain in the channel, that is in the horizontal direction, that is the most prominent electric field, and electrons are moving because of that electric field. We are neglecting the vertical electric field. But in this case, if we have large VGS, then in this case we have large vertical electric field. In gradual channel approximation, while we were deriving the expression for ID, at that time we were neglecting this vertical electric field. Go back to the assumptions of gradual channel approximation, you will find that. Okay, because of this large vertical electric field, there will be a lot of scattering in the at the interface, the oxide semiconductor interface, in the inversion layer where the channel is formed. Okay, because of the scattering, because of this diversion of path due to this two types of electric field, the mobility of the electrons that were moving from source to drain, that will change. Okay, mobility basically degrades, it decreases. It was trying to move in this direction, it will scatter in all these directions because of the vertical electric field, and overall mobility will decrease. So overall our current will decrease, right? So because of that, mobility degrades. At the channel. Specifically near the interface. Near the surface of the p-type silicon. Okay. Because of this, our drain current decreases. You see, there is a direct dependency with mobility. Okay. Next, again, this is a very important effect, non-ideality, or the, you can say, the result of scaling is that in case of short channel MOSFET, there is one term called VT roll off, that threshold voltage decreases. Why it decreases? So threshold voltage, the expression is that we have this flat band voltage minus QD by COX plus 2 phi f, right? In case of NMOS, this depletion charge is negative, so overall this is a plus, right? So how it happens? What is threshold voltage? We apply a positive gate voltage first to deplete this area like a MOS capacitor. After depletion, we do the inversion, that is the 2 phi f part, and after inversion there may be extra inversion charges because of the more gate voltage, and that we add with another term is like Q inversion by COX, right? You can add this QD plus Q inversion, something like that. Basically what we do, what is the process of this threshold, is that we deplete the area, then we create inversion. Okay, first we remove the holes, then we create the channel of electrons, right? Now that is for MOS capacitor. What happens in MOSFET, we have the source and drain regions. This is source and drain, and we have said that these two junctions, this N plus P and N plus P junctions, are always in reverse bias. We know that in reverse bias, the depletion region is present in PN junction even if it is a reverse bias or forward bias. As soon as we connect to P and N semiconductor, there will be a depletion region. Initially there will be movement of carriers because of diffusion, and then there will be a creation of depletion region, and that basically it does not allow the diffusion process anymore, right? When we apply forward bias, we reduce the depletion width and we allow some flow of carriers. When it is in reversed bias, the depletion width widens and there will be no transfer of carriers, right? There will be no current, ideally zero current. Nothing is ideal, there will be some current, but there will be a wide depletion region. So because these are in reversed bias, there will be a depletion region here, and we are depleting the channel here, so there is a depletion region. Now a certain depletion area, depletion region actually overlaps the channel depletion region, and the depletion region of these source bulk or drain bulk junction actually overlaps. So some of the depletion charges are actually coming from this N plus P junction, not from the applied gate voltage. Okay, so total Q depletion, I can say that some are coming from VGS because we are applying positive VGS, so holes are moving away because of that, and some are coming from source body or drain body junction. Okay. Say overall this area is L, channel length. You can see this depletion region is coming from this junction, this depletion charges are coming from this junctions. Okay. To Therefore, to deplete the region below this gate oxide layer, we actually need less gate voltage. Okay, some depletion charges are already present due to these reversed wire junctions. Okay, so some depletion charges. Are coming from source body or drain body junction, not due to VGS, right? And this is known as charge sharing effect. Okay, some charges are shared between these depletion regions and the channel depletion region, and because of that, overall our threshold voltage decreases. Okay. Yeah, we don't want a very low threshold voltage again, because again our ion by I of ratio will be less, so that is why we do some other things like increase the doping concentration, so that overall we get a higher threshold voltage. Okay, this is one effect of short channel effect. Another effect, another type of scaling is also like we also changing our width, not only length. So when we change W, that is known as the narrow channel effect, and because of narrow channel effect actually there will be an increase in threshold voltage. Why? So let's see, I don't know how much time I have taken. Okay, I have this one topic, and then okay, first I will discuss drain induced barrier lowering. This I have taken from the lecture notes. Again, this is one effect for one non-ideality in short channel effects. So this is the energy band diagram for a normal long channel MOSFET. Okay, so this is the source side, which is N plus. So the Fermi level is close to the conduction band edge. This is the drain side. Okay, this is also N plus. So again the Fermi level is close to the conduction band edge when we are not applying any voltage. If we apply a VDS, so there will be a change in the band diagram. We are applying positive voltage, so the bands will go below, right? Fermi level will go below. So this is what is showing. So we are applying VDS some greater than 0, and that is why there is a lowering of bands. Okay, and there is this channel in between. Now electrons when try to move from source to drain, there is this barrier. Okay, now when we apply here like a gate bias, basically this channel barrier will change, so this will decrease. When we apply a positive bias, this will decrease, so overall electrons can pass through this layer. Okay, there will be a flow of current. But what happens when if we are applying a large VDS? Okay, large VDS, and especially in case of short channel. So for long channel, even though we are applying a large VDS, the Fermi level has moved to a very lower value, but overall there is still a large barrier. So if we not apply a gate bias here, so electrons from source side cannot move, right? Cannot move. But what happens if it is a short channel? So as it is decreasing, you can see the channel barrier is also decreasing. So either electrons will be able to tunnel through it. I mean, there is a chance that electron can pass through it, and overall you can see there is a lowering of barrier, so electrons can pass through it even if the gate voltage is not sufficient. Okay, so what it means, even though our threshold voltage is not reached, in case of say for long channel MOSFET we have some threshold voltage, but for the same kind of configuration, if we have a long channel, because of this large VDS and because of this decrease in the change in the Fermi level, there is a barrier lowering, and because of that, even though this value of gate voltage is not achieved, electrons can still pass from source to drain side. Electron can still travel from source to drain side. I'm not sure whether you are being able to understand this or not, but please look at this band diagram. Is that there is a change, there is slightly decrease in this barrier in case of short channel effect, and because of that, actually in case of short channel, VTH decreases. It does not affect much even if we apply a large VDS for long channel device, but if it is a short channel device, if we apply a large VDS, there might be a barrier lowering, and because of that, even though we are not applying sufficient gate voltage, current will still flow. Do we want that? We don't want that, right? We want current to flow from source to drain if only we applying a gate voltage which is higher than certain threshold voltage, right? But that may not be valid in case of short channel. There may be a barrier lowering because of VDS. Okay. VDS we are applying just so that electrons can pass from source to drain. Whether our channel is on or off, that we are controlling from gate voltage. Okay, so without gate voltage we don't want any flow of current due to VDS, but in short channel there may be some flow of current because of VDS also. So this is the drain induced barrier lowering, and in case of narrow channel effect, I don't have much time, I should go to the questions also. Please go through the lecture videos. If you have not studied yet, then you can go through it again. Because of that, if the channel length is narrow, because of the filled or the certain depletion region below the filled oxide also, the threshold voltage actually increases. Okay, for short channel, threshold voltage decreases. Why? We have discussed, because of the charge sharing, and for narrow channel it increases again because of the depletion layer below the filled oxide regions. I try to discuss all the topics before going into these questions, because then I don't have to explain much. Okay, you will be able to answer from your side also. I will write down the questions. Consider an N-channel MOSFET where WLL, which are channel length and width, are reduced by 30%. That means our scaling factor alpha is 0.7, the typical condition that we are discussing. And both the supply voltage VDD and threshold voltage VDH also reduced by 30%. When the transistor is connected to a load capacitor, it is found that the capacitance and delay are reduced by 30%. What is the dynamic power dissipation? So we have already discussed all of these. Just give you the solution. So basically the scaling factor is 0.7 or 30%. Okay, and we have to calculate what is the reduction in dynamic power dissipation. Okay, should not consider all disconnected to load capacitor. It is found at so we know the formula P dynamic power dissipation. This is CV square into F, okay, which is CV square by T delay. Okay. So the capacitance and the delay are reduced by 30%. V is also reduced by 30%. Everything is reduced. So overall, how it is affected, I've already discussed it. This. So 0.7 into 0.7 square reduced means we multiply by 0.7, right? T is also reduced. So multiply by 0.7, so this is 0.49 in percentage. So how much it is reduced? New dynamic power is 49% of original power. So how much it is reduced? 100 minus 49, so that is 51%. Okay, so my answer is A. question. Okay. There are two statements given. So the first statement is so this is the first statement. The next statement is there are few options. I will not write down the options. The question is which of these statements are correct. Okay. So whether S1 is correct or not. So typically the channel lengths of a short channel MOSFETs are much larger than the depletion width of the source and drain junctions. This is false, right? So XD is comparable to the channel length in case of short channel MOSFET. So S1 is false. S2, the current in short channel MOSFET shows significant deviations from square law theory. So we know that in case of long channel MOSFET, our ID set is given by in the saturation regime mu COX W by 2L VGS minus VTH square, right? So there is the square dependency, and that is the square law theory. In case of short channel MOSFET, what happens? ID is directly proportional to VGS, right? We know the expression mu n COX W by L VGS minus VTH into VDS. Please check this expression from the lecture notes. Not exactly sure. N will definitely not be there. N will not be there. Please check this expression, okay? Whether this mu, okay, mu will not come, right? Velocity saturation happens. That is why this VD set is coming, right? So mu is not there, COX W VGS minus VTF, and this is VD. Okay. Yeah, VD set, the velocity set, L will go away, and this is the WCOX. Okay. But please check this expression once again. So statement 1 is 2 is true, right? There is a variation of the square law theorem. S2 is true. This VD, so this is a small v. I mean, this is the drift velocity. I try to write drift velocity or velocity with the small v and voltages with capital V, so that there is no confusion. If I am missing somewhere, please remind me that this is not the capital V, this is the small v. So this is the saturation velocity. Okay. I'll write down the question first. I should have included the figures, but I will try to draw it as close as given in the questions as possible. Okay. Identify the type of MOSFET. Corresponding to the curves given in the figure. The graph I should have copied earlier. I'm sorry, I forgot to do that. I will try to draw the graph as given, as close as possible. This is VDS. this is ID, so this is the output characteristics of a MOSFET, right? What is the transfer characteristics of a MOSFET? ID versus VGS. Okay, that is known as the transfer characteristics. Remember I told you that when we write this word transfer characteristics or conductance, we are taking one from one side, input side, one from an output side, right? Here our both VDS, that is like it's kind of like our output side. VGS is our input voltage. ID is our output current. So that is why when we plot ID versus VGS, we have this term like transfer characteristics. This is the output characteristics of a MOSFET. So MOSFET 1 has slightly higher current and constant ID. Okay. MOSFET 2 has lower current, lower VD set, and slight increase in current in the saturation region. So this is my MOSFET 1. This is MOSFET 2, and this is for VDD, which is equal to VGS, which is equal to 1.8 volt. Now based on this graph, which one, MOSFET 1 is what and MOSFET 2 is what? Okay, we have already discussed a lot about short channel and long channel MOSFET, right? What are the non-idealities in short channel MOSFET? So by looking at these graphs, you can say that our MOSFET 1 is long channel MOSFET, MOSFET 2 is short channel MOSFET. Why? First of all, ID set is almost constant in case of long channel MOSFET. In case of short channel MOSFET, because of channel length modulation, we know that in the saturation region also our current increases slightly. Okay, so channel length modulation effect is more prominent in case of short channel MOSFET. That is one reason. In case of okay, so the values are not given here. Sorry, I cannot like use the scale here, so I'll just write down based on this. So follow square law theory. Okay. And ID value is also higher. ID saturation value is higher compared to short channel MOSFET. What happens in MOSFET 2? ID increases slightly, in saturation regime and also there is a deviation from square law theory. This value and this value is not same, so this is a short channel MOSFET, and also our ID value is much lower, okay, because of all this effects like mobility degradation and all these things are more prominent in short channel effects, so ID value is less, so this is a short channel MOSFET. Assignments or in exam, when this kind of a question is given, in that case the scale will also be given. You can roughly calculate, so VGS value is also given, okay. VTH value, if the VTH value is also given, you can check whether this VD set is close to VGS minus VTH or not, okay. If it is close to VGS minus VTH and the graph also looks like long channel MOSFET, then you are confirmed, right, that is a long channel MOSFET. But if the saturation value is much lower and VGS minus VTH value is much higher, and also the graph is something like this, then you can also be confirmed that okay, this is a short channel MOSFET. Okay, here the saturation is happening due to velocity saturation effect, not due to pinch off, okay. So this saturation is happening due to pinch off here in MOSFET 1. This is due to velocity saturation, remember that. And how you can verify? You can check VGS minus VTH value and compare with the VDS set value, okay, if all the values are given in your graph. We have discussed that the threshold voltage in case of short channel MOSFET actually decreases, okay, compared to long channel MOSFET. The question is, what is the primary mechanism responsible for reduction of threshold voltage? Okay, I will give you the answer, and also we will briefly discuss what are the other mechanisms. Okay, the answer here is C. drain induced barrier lowering, that is the primary mechanism that actually uh, responsible for reduction of threshold voltage. Okay. What are the other mechanisms? So we have discussed about the charge sharing effect. Okay. Why the threshold voltage decreases? Because some amount of depletion charge is actually coming from the source and drain junctions. We actually try to make reduce this effect by increasing the doping concentration. Okay. That is one way. In case of scaling, when we do scaling, we change the doping concentration also. How it can be again decreased? One way again is that, you remember, we always try to keep the source and drain junction reversed bias. Okay, this is our source terminal, this is our drain terminal, this is the gate terminal. We have another terminal, that is the body terminal. We bias the body terminal in such a way that this source body and drain body junction is always in reversed bias. Okay, so for that, either, so this drain current, drain terminal, we connect it to positive voltage, right? So this n, this is n side, it is connected to positive voltage, so body is normally grounded, so this is the reversed bias condition is satisfied, right? Mainly we want a higher voltage, higher or equal voltage in source and drain terminal compared to the body terminal, because this is PC level. If the body is at higher potential or at higher voltage value compared to source and drain, then it will be a forward bias, right? So in case of MOSFET, we either keep the body as ground or we apply a negative voltage so that this is in reversed bias. Say normally we connect it to source which is grounded, so this is 0 volt. What if we apply a negative voltage? Then this again there will be more depletion region, right? We are applying more, we are kind of applying a more reverse bias voltage, something like that, right? So again the depletion charge will be more, and because of that also threshold voltage will decrease, right? So these effects we try to nullify, like again based on doping concentration, and normally we try to connect it to the source terminal so that these are reversed bias, but depletion width is not that much. You know, another problem, I was not discussing it earlier, if we have a very large depletion region in this source and drain junction, there is another problem that may happen. So if say this depletion region increases is too much, and then there is no like a proper differentiation between the depletion region and source and drain, then there is a kind of like a large depletion region that kind of might happen. So this is known as punch through. You can look into it. That is one problem that may also happen in case of this MOSFET. So we don't want that, because of punch through, instead of the channel there will be a large current here because of this junction breakdown kind of situation. Okay, so again we are careful with that. We don't want to keep this is in reverse bias, but it's not, the depletion width is not high, that much of high that our threshold voltage is much affected. It's not much affected by the depletion width of this junctions. Okay, again the threshold voltage also depends on the gate drain capacitance, that also another parameter, because if you remember the threshold voltage expression, this is B flat band voltage minus QD by COX plus 2 phi f, right? So this also depends on the capacitances. Okay, but we don't want to, we also reduce it and scale it in a such a way that, and also we use like high K material and all these things in such a way that the threshold voltage is not much affected due to the we scale it, but not much due to this gate to drain capacitance. Okay, we have the control of all other parameters that is in our hand. But what will happen if we apply a large VDS? Then, because of the drain induced barrier lowering, the threshold voltage reduces. We don't have much control uh, over this DIVF thing. Rather than, I mean, we can have, the only option is that we don't apply a large this voltage. Okay, so the primary mechanism is because of this. Other trains, we try to keep it in our hand, keep it under control. This I have not discussed now, but if you have gone through the lecture videos, then we already know. We'll discuss about this question. Strained silicon is used to improve MOSFET performance. How does it enhance device characteristics? Particularly in terms of carrier mobility. So this was discussed in the last lecture videos, I guess. We are moving from traditional long channel MOSFET to short channel MOSFET, different kinds of scaling, different ways to scale, and now there are some other devices to improve the overall performance. Okay, one way when people are trying this strained silicon. So what is strained silicon? There is some kind of strain is applied to the material of silicon. Okay, either compressive or tensile. Okay, like different other materials are deposited. Please go through the again lecture notes. There are different configuration to have different kinds of strain on silicon. Okay, with different material, and because of different material the silicon will go. So what happens is that how this kind of strain arises normally in materials. Suppose you have some material, okay, it has some lattice structure, it has some lattice constant. Okay, if we grow another material on top of it that has a slightly different lattice structure, say, then there will be some deformation in the material. Okay, that basically give rise to a strain on the material. Okay? Because of the stress and strain, you can see there is a change in the lattice constant. Okay, I don't know whether you remember this or not, but we have discussed earlier about the band structure of material. Okay, if you remember, we have this EK diagram. This is EK. This is not band diagram, this is the band structure. Okay, EK relation. There we have said that there is this direct band gap material, indirect band gap material, and based on this EK diagram we define it. Okay, now this EK diagram we actually comes from the lattice arrangement, of the atoms in a crystal. Now if that arrangement changes, the lattice constant changes, there will be a changes in the band structure. When there is a changes in the band structure, some properties of the material, the fundamental properties of the material changes. Okay, so what happens when we change the band structure? Mobility, actually the concept of mobility comes from the band structure. Okay, I think we discussed this in initial week 1 or week 2 videos where we studied about quantum mechanics and all these things. The point is that the only thing you should remember, when there is a stress or strain in the, whether it is a compressive, whether it is a tensile strain in the material, the lattice constant or the gap between the atoms in the material changes, and that changes the band structure, and as it changes the band structure, some fundamental properties of the material changes. Now in case with strained silicon, in MOSFET, how we are actually improving the MOSFET performance, we are actually changing the mobility of electrons and holes in strained silicon. And you know that in the current expression, current is directly proportional to the mobility. Whether it is a long channel or short channel, we use this mu COH W by L, this term, right? So with strained silicon, we are changing the mobility, and as we change the mobility, mu values, and we are changing the current. We are basically improving the ID, the drain current in silicon MOSFET by applying some strain. Okay, please go through the lecture videos. I think it will be more clear from the figures of the of different devices how people are trying to improve the performance beyond scaling. Okay, we are not in the regime like we are only changing the dimensions to improve the current, improve the delay, improve the power dissipation. People are trying all kinds of different technologies to improve the performance of MOSFET. So the solution is in strain silicon, mu actually increases. Okay. The electricity is gone. I hope that my net is working. Okay. Okay, let's not take more questions. It's already 7:52. Don't know what happened to electricity. If you have any doubt, you can ask me, or we can briefly discuss about the this other type of technology that was discussed in the class, like uh, why we are going from traditional MOSFET to FinFETs and gate all around. I'll briefly discuss that. I hope that my laptop will work and the net will Wi-Fi will work. Okay, can't see anything. Okay, yeah, it's better. This is not a question. Okay, so nowadays, what is a new technology? I don't know how. I mean, the using the word new in case of technology is very tricky because they become old, very fast. So one technology is this FinFET, where instead of like a planar device, there are certain fins, right? And gate is kind of all around this fin. Please look at the diagram or search in Google. I will not be able to draw it properly. What are the advantages of these technologies? See, what we want in transistors, we want to control the current of the channel. This I have explained, like I have talked about this multiple times, is that in case of MOSFETs or in case of transistors or in case of any semiconductor device, we want to control the current as per we want. And how we control the current in case of MOSFET, especially in case of enhancement type MOSFET, we apply a gate voltage. So we want our current conduction to happen only when we apply a gate voltage, and only when the gate voltage is higher than threshold voltage. Now with the MOSFET scaling and with the device dimension scaling, you know that there are other terms like tunneling and all this are happening. And basically our ion by eye of ratio may deteriorate. Okay. In case of FinFET or gate all around transistors, the control of gate is much higher compared to a short channel like a MOSFET, which is like scaled down with using the scaling like whatever the convention that people are following. uh, in case of FinFET and gate all around, the control of a gate is much higher. That is why people are moving from traditional MOSFETs to these technologies, because using this technology we are having small devices. We are getting all the advantages of MOSFET scaling, and as well as we have like higher gate control over the channel. Okay, we don't want current conduction in the channel without the gate control. And when we have this gate all around kind of a structure and we have this fins, we have more control over the gate. The gate is like around this fins. Okay, so the current conduction is happening through the gate. Okay, please go through this advanced technologies if you are interested. I don't have much time, and it will be better if I stop. If you have any quick question, then you can ask. Otherwise, I will stop the session here because the electricity is not coming back. Okay. I have few more questions. Um, I will not do it today. We are going to have one more extra session apart from the regular sessions. I can discuss those questions on that day. Okay, you will be notified by NPTEL team when we will have the extra session. Okay. If there is no question, then thank you. Let's meet in the next Tuesday. I will stop the session here.